Okay, good morning to everybody. Before going on with the last topic concerning the Sommerfeld model, I just wanted to add a comment concerning the last calculation that I made last Tuesday. At the beginning of the calculation, when I wrote down the equation concerning the variation of the distribution function, I told you that the variation of the distribution function was due to two contributions. One was the one concerning the number of electrons that are lost due to collisions, and that number was equal to minus f, where f is proportional to the number of electrons that you have in a specific position with this fixed quantum numbers, times the probability that those electrons suffer a collision. And the probability to suffer a collision in amount of time equal to dt is dt divided by the relaxation time. Then I told you that at this point you should estimate how many electrons are added to the value of the actual number due to collisions that take place in other places, but has as an output one electron in corresponding to those specific parameters. And I told you that that number was equal to plus f0, where f0 is the equilibrium distribution function times the probability to suffer a collision in that short amount of time. Just to add an additional justification to that f0 times dt divided by relaxation time, just think about what happens if you are at equilibrium. So at equilibrium, you have that, in principle, you should evaluate the variation of the equilibrium distribution function. So we should write df0. But if we are at the equilibrium, we know that df0 has to be equal to 0, because that is the distribution that describes the equilibrium condition. So this should be equal to 0. And the equality to 0 is due to the fact that we are in a stable state, so no variation, no change with respect to the equilibrium. At this point, using the same way to, let's say, consider the initial calculation, at this point, we should write df0 as the sum of electrons that are lost due to collisions and electrons that are gained due to other collisions. In this case, using the same method that we used to write down the first term here in the previous equation, then the number of electrons that you lose is equal to minus the actual value of the distribution, that in this case is f0, times the probability that those electrons suffer a collision. At this point, then we have to include another contribution, that is what we gain from collisions. But if the result is to be equal to 0, then what we gain from collisions has to be exactly equal to what we lose from collisions. So due to that, here we have to include plus f0 times dt divided by relaxation time. So the first term has exactly the same justification that I used to justify minus f times dt divided by relaxation time. The second term at the equilibrium has to be there, because that has to be exactly equal to the initial term. Otherwise, df0 is not 0. So in this case, we may say the number of electrons that we lose, let's say what I called out, so the electrons that are outgoing from the specific place where we consider the value of the distribution function, in this case, has to be equal to the number of incoming electrons, again, to preserve equilibrium. The first term is due to the actual distribution function. Now, if we want to go to a general situation, the first number depends on the actual value of the distribution function, because that is what you lose. Due to the fact that what you gain is not depending on the previous distribution function, due to the fact that collisions erase any information concerning what happened before the collision itself, then at that point, we have no reference to evaluate the number of incoming electrons. Due to that, to evaluate that number, we may refer to the only situation we know, and that situation is the situation at equilibrium. And in this case, we use F0 due to the fact that we know that after the collision, the electrons are taken back to the equilibrium condition. So no memory of any previous effect that was applied before the collision. So due to that, we may use this term here as an estimate of this term here. So I wanted to compare these two situations just to say, in the second situation, it's easier to understand why I put plus F0 times dt divided by relaxation time. Then I export that situation to any other situation due to the fact that since I'm not able to estimate what happens after the collision, because that does not depend on going back to the previous case to F, because F at that point has no influence on the electrons, then the only thing I may do is to refer to F0. So that's why I put plus F0 times dt divided by tau in the equation concerning the variation of F, even when F is an arbitrary distribution function that corresponds to an aqueous state of the system. So that was just to add a justification, an additional justification to the plus F0 times dt divided by tau, a term that I used at the beginning of the calculation concerning the conductivity in the case we apply in an external electric field that is uniform and does not depend on time. And due to the fact that the final point of the calculation was that even in the Sommerfeld model, we have that the conductivity is equal to the, let's say, sigma 0, the conductivity when E is constant and uniform. We have that sigma 0 is electronic density E squared relaxation time divided by the electron mass. So if in this case we have exactly the same result that was obtained with the Drude model using exactly the same conditions, let's say static electric field, then we expect to obtain exactly the same results even when we consider what happens when we apply an electric field that depends on time, or when we want to consider what happens in the whole configuration. So the final conclusion is, even if in this situation F, referring to what I just wrote before, even if F is not the Maxwell-Boltzmann distribution, but is the Fermi-Dirac distribution, and so the electrons are considered as, let's say, quantum mechanical particles, so are described not by a position, an equation of motion, but are described by a wave function or a combination of wave functions, then concerning their properties in the conductivity again, Hall coefficient, and so on, then nothing changes with respect to the Drude situation. So the conclusion is, if we were not able to explain what happened concerning, for instance, the temperature dependence of the resistivity, or actual value of the Hall coefficient, or optical properties in the Drude model, we are not able to give more details, even if we switch from the Drude case to the Sommerfeld one. So the idea is just changing the way of considering, of handling one electron is not enough to change the conclusion of the model concerning the conductivity properties. In particular, the underlying problem is that we are still considering the second law of dynamics as the main equation concerning how to understand what is the effect of an external field over the electrons when, again, we consider the electrons within the metal. So that is the main problem of the situation. And just to conclude to conclude the comparison between the Drude case and the Sommerfeld one, what we miss now is the evaluation of the specific heat in the case of the Sommerfeld model. So the last step now I would like to show you is how we evaluate the specific heat in case we consider not Drude electrons but Sommerfeld electrons. The Sommerfeld electrons, now concerning this specific term, one step back. The specific heat depends on the total energy of the system, in particular on the energy density of the system, and is related to the temperature dependence of the total energy of the system. In principle, if you want to obtain the exact calculation and to if you want to obtain the exact value of CV in the case of the Sommerfeld model, you should write the total energy of the system considering the, so if you want to evaluate U, you should write, for instance, an integral. We may use the G of E, the energy density of the levels. Then we need the F of E, and in this case, it's not used. Let's say we have to consider the explicit temperature dependence of the distribution function, because we have to evaluate how the total energy depends on the temperature so that we may evaluate the derivative. And what we are summing up is the energy. So in principle, you should evaluate that integral to find U of T, and then you make the derivative and you find the specific heat. This calculation can be done, but needs some approximations due to the fact that G of E and E are, let's say, polynomial functions, so they are easy to integrate. But F of E includes the this term where we have the exponential at the denominator. So the full integration, so the full evaluation of U is not, let's say, something you do in just 2 or 3 steps of calculation. And just a comment concerning why I wrote EF. I told you that EF in principle is the value that the parameter. So at T equal to 0, the chemical potential is exactly equal to the Fermi energy. But if the temperature changes, then the chemical potential decreases with temperature, decreases with respect to EF. So in principle, it's not correct to write EF in this equation. But due to the fact that what I expect is that the variation of T, sorry, the variation of the chemical potential with respect to EF is in the second order. So the variation, the change of mu with respect to T, the variation, sorry, of the value of the chemical potential with respect to EF is in the second order of T, due to the fact that this calculation is done to evaluate the specific heat, let's say, at low temperature, room temperature. So let's say not at 2000 Kelvin, but just, let's say, some hundreds of Kelvin. At this point, I expect that KT is small because I'm doing a calculation where KT is of the order of some tenths of EV. Since EF is of the order of some EV, I expect that this ratio is very small. So due to that, I just wrote EF in the integral and not chemical potential, just to let's say, stress the fact that I'm expecting to make the calculation when at the value of the temperature, so that I may confuse I may use EF in place of the actual value of the chemical potential. Anyway, due to the fact that the calculation needs some time to be done, I just would like to make another way. I just would like to use another approach to the evaluation of CV that is shorter for what concerns the calculation, but is more focused on the physical mechanism that brings you to the value of the specific heat. So let's say if we want to evaluate so if we may write U of T, that is the energy of the system as a function of temperature, as U at T equal to 0. So the energy of the system that we have in the situation that I just wrote here in this diagram. So when the Fermi function is a sort of step function, 1 below EF, 0 for energies that are higher than EF, plus the variation, so the contribution due to the fact that with respect to T equal to 0, when the temperature is T different from 0, then the shape of the distribution is not exactly the step function that I have here, but is something slightly different. So in this case, this is the T equal to 0 situation, and this is the T larger than 0 situation. So at this point, due to the fact that CV does not depend on U at T equal to 0, because that is just a constant term. So when we make the derivative, that term disappears. We may just concentrate on delta U, delta energy. So I just would like to focus on delta U for the calculation. Delta U, so the variation, the change in energy due to the fact that the temperature is not 0 but is T, is proportional to what? Is proportional to, let's just look at what happened here. If you compare the diagram corresponding to T equal to 0 to the diagram corresponding to T larger than 0, you observe that here in this region up here, you lose electrons, because those electrons, the probability to have those levels occupied is no more 1, but is smaller than 1. So you have a number of electrons that is smaller than 1 in those levels. But on the other side, you also have additional levels corresponding to an energy that is larger than EF. So you have that you have shifted some electrons from levels that are below EF to levels that are above EF. So this shift of electrons produces the fact that you have an increase of the energy of the system, because some levels that before were not populated now are being populated by electrons. So what we need to do now is just to estimate the increase in the total energy due to the fact that those electrons moved from low energy levels to higher energy levels. What is the number of electrons that have, let's say, changed their condition? The number of electrons is related to, let's say, the range of energies where we observe this deformation. This deformation is obtained in a range of energies close to EF that has a width that is proportional to KT, because as we saw, when you increase the temperature, the range of energies where you have the deformation from step function to the actual function is of the order of KT. So this range of energies is proportional to KT. We know the expression for the energy density of the levels. So if we know G of E and we multiply G of V by the width of the energy range where we observe this modification, then we have an estimate of the number of electrons that are found in that range of energies. So G of V times KT, this is proportional to the density of electrons So that is proportional to the density of electrons that change level. So due to the increase on temperature of the temperature, those electrons move from the let's say from this configuration, so from the occupancy of the levels below EF to the occupancy of the levels above EF. To be more precise, since KT in general is quite small with respect to EF, we may say that G of V is actually G of EF because the range of variation of KT is very, very small with respect to the width of the distribution. So I may write G of EF in this equation. So this is the number of electrons, or is proportional to the number of electrons that change the occupancy of the levels. Then what is the increase of energy corresponding to those electrons? Those electrons have moved from the, let's say, upper left, the upper left area that is highlighted in that diagram to the bottom right area that is highlighted in the same diagram. So the order of magnitude of the change of energy is again proportional to KT. So on average, one electron that is on the, let's say, on the left side shifts to the right side and makes a change of energy of the order of KT. So this, to evaluate the total variation of energy, I have to multiply the number of electrons per unit volume for the, let's say, typical energy that correspond to the variation. And that typical energy is, let's say, proportional to KT. Since G of EF is 3 divided by 2 times electronic density divided by EF, and here I remove the ratio between the energy and EF because that ratio in this case is equal to 1, and then I have KBT to the power of 2. So if the increase of energy is proportional to T to the power of 2, then if I evaluate the specific heat and I make the derivative with respect to T, then I have that CV using exactly the same expression is equal to 3 divided by 2 times N divided by EF times KB squared times twice the temperature. So what we find here is that the specific heat of the electron system is proportional to T. So it's proportional to the temperature. And just to, let's say, please consider just, let's say, the aim of this calculation was not to find the actual value of CV, but the aim was to find in a, let's say, in a short, just with a short calculation, what is the actual temperature dependence of the specific heat. So the idea behind this calculation is just to understand, just with the short calculation, what is the expected temperature dependence of the specific heat. So this is just an approximate value. This is not the actual value. But the important thing is that even if the coefficients are not fine, the temperature dependence is fine. So if we had done the full calculation, then again, this is just an approximation. So in approximation, so the important thing here is the T dependence. if I just make the last comment, the physical, let's say, comment concerning the actual expression of CV, so the let's say the full calculation if you do that, then the actual value of so the actual value is pi squared divided by 2 times kBt divided by EF times the electronic density times the Boltzmann constant. So again, we have that CV is proportional to T. What changes is just the coefficient. But in this case, I would like to focus not on the coefficient, but on the temperature dependence. Why the temperature dependence is so different with respect to the Drude configuration? So what is the main physical motivation behind the fact that here we have something that is proportional to T? So in principle, when T is equal to 0, the CV here is 0. Differently, in the Drude case, when T was equal to 0, the CV was not equal to 0, but was something that was half of the value of the specific heat of the solid when we consider the let's say the saturation value of CV. I just changed page to rewrite the equation and just stress on the physical mechanism behind this change of value. Sorry, I just had to restart the blackboard. Are you still able to see the main page of the blackboard? I make this question to those who are connected. Okay, thank you. So what we saw is that this is pi squared divided by 2 times kBt divided by EF, and then electronic density times kB. The important thing that allows us to understand why we have this difference we may just rewrite the expression of CV. So if we consider that the electronic density can be written as the molar density times the Avogadro number, and the Avogadro number times the Boltzmann constant is the constant of gases, then this can be written as pi squared divided by 2 times kBt divided by EF times the molar density of the electrons times the constant of gases. In the Drude case, CV was equal to 3 divided by 2 the molar density of electrons times the constant of gases. So this term here is equal to this term here. Then we have, let's say, a coefficient, and here again we have a coefficient. It's not the same coefficient, but let's say the order of magnitude is always unity or close to unity. What changes most is this fraction. This fraction is the ratio between the thermal energy to the Fermi energy. If you look at the diagram of F as a function of E, that is equivalent to the ratio of the, let's say, energy range where we expect to observe a variation of F0 when we switch from T equal to 0 to T different from 0 to the Fermi energy. So this ratio is the interval of energy affected by T, so by the temperature, divided by the overall range of energy where the electrons, let's say, are observed. So this ratio is a sort of indication of where the change of T affects the distribution. If you consider all the electrons that are found here in the area, this area, that, oh, sorry, I moved the sheet. Oh, okay. I'm sorry, but I made a rectangle, and the rectangle is slightly shifted with respect to the diagram due to the fact that I moved the sheet while I made the rectangle. So it just that is the motivation of that shift. There's no physical motivation behind that. So the idea is, as for all the electrons whose energy ranges from 0 to, let's say, EF minus KT, nothing changes because the occupancy of those levels is always equal to 1. Those levels do not contribute to the value of the specific heat because there's no energy variation for those levels. So at the end, from the point of view of the electrons, let's say the number of electrons that is actually useful for CV is just the number of electrons that we have close to EF. And that number of electrons, so is KB divided by T, sorry, KBT divided by EF times NM. So the number of electrons, sorry, the density of electrons that contributes to the specific heat is not NM, but is NM times this fraction. And due to the fact that that fraction is very small, because KT is smaller and smaller with respect to EF, then the actual number of electrons that participate to the specific heat, that contribute to the specific heat, is actually very low. So the important thing is that also in this situation, we observe that thanks to the fact that the electrons has to follow the Fermi-Dirac distribution, and the Fermi-Dirac distribution has the dependence on the energy that is represented in that diagram, then not all the electrons participate to the specific heat, but just a small number of those is actually contributing to the value of the specific heat. And from the point of view of the experiment, if you want to measure CV as a function of T, you find that at high temperature, we have the long empty value that is 3 times molar density times the constant of gases. Then you have a decrease. You have a range of temperatures where the dependence is proportional to T to the power of 3, but we also have a range of energies, sorry, a range of temperatures where the dependence is actually proportional to T. So let's say now we know something more than we knew with the root picture, since we are still not able to predict the full dependence of CV as a function of T. But at low temperature, it is actually possible to detect a range of temperatures that we will estimate in the next weeks, but is of the order of, let's say, 5-10 Kelvin, no more, whereas the CV dependence is actually linear. So just to make a rough estimate, since this ratio KBT divided by EF is very small, what we expect is that the electronic contribution is actually there, but the slope of that line is very small. So apart from the initial regime where the CV is small in absolute value, so at that point, even if the contribution of the electrons is small, then you notice that because the average value of CV is small, then as soon as the CV approaches the Dulong NPT value, at that point, that value is very large with respect to the electronic contribution. So from that point on, you completely lose the sensitivity to detect the contribution of the electrons, and you just appreciate the contribution of something else that for the moment we have not still evaluated, but the contribution of something else that gives you this dependence that approaches the Dulong NPT value at high temperature. So it's nice to have been able to detect something that we didn't know before, and there's an actual equivalent in the laboratory, but we still miss the description of the main part of the dependence of CV with respect to T. And before concluding this part, I'd like to stress again the fact that thanks to the shape of the Fermi-Dirac distribution, also in this condition, the main contribution to something, and that something in this case is the specific heat, is just due to the electrons that have an energy that is close to EF. And this is something that we will see in many different situations. That is the fact that even if you have a huge number of electrons in your system, at the end, the number of electrons that affect the macroscopic properties of that system are not all the electrons you have inside your metal, in this case, but are just a small fraction of those. And in this case, the fraction is proportional to KT divided by the Fermi energy. Okay. Are there comments or questions concerning this part? Okay, so with this calculation, I just wanted to conclude the section devoted to the Sommerfeld picture, to the presentation of the Sommerfeld picture. That in part, I think you have already seen. And I would just like to summarize briefly what we found before switching to the next way to describe the properties of the electrons in the solid. That is the way that we will use nearly till the end of the lessons. And yeah, just to summarize, in the Sommerfeld picture, the only thing that changes with respect to the Drude picture is the fact that now we use the Schrödinger equation to describe the electrons. So we introduce, in this case, the term level to fix the properties of the electrons. And in this picture, the electrons, as they are fermions, have to follow the Fermi-Dirac distribution. So this is the main variation between the Drude picture and the Sommerfeld picture, and that was due to the fact that in the, let's say, 25, 26 years between the presentation of the Drude model and the presentation of the Sommerfeld model, what was known let's say what was known. What was introduced was the quantum mechanical picture. So the Schrödinger equation, uncertainty principle, the Pauli exclusion principle, and all those information, all that information was included in the model. The main effect that we have concerning the electronic system is the fact that, let's say, EF, that is the maximum energy. Let's say just to make simple the discussion, if we supposed to be at 0 Kelvin, the maximum energy that one electron has in the system is equal to EF, and EF ranges, let's say, if you pick up all the possible elements in the periodic table, ranges from 1.5 eV up to 15 eV. So let's say is of the order of EVs, more or less. And this energy is very large with respect to the, let's say, typical energy that one electron had in the drawn picture. This change, so the fact that the typical energy of one electron increases that much, is due to the Pauli exclusion principle that is included, let's say, that is included in the Fermi-Dirac, in the shape of the Fermi-Dirac distribution. So at that point, the occupancy of the levels, as soon as you let's say, include electrons in your system and you occupy levels, also including the spin of the electrons, then you start from occupying the low energy levels, and as soon as those levels are occupied, then you need to occupy high energy levels. So due to that, what we observe in the wave vector space is that the electronic levels occupy a sphere that is the Fermi sphere. And what we know is that the energy of the electrons is proportional to the square of the wave vector of the electronic wave function, and also the velocity of the electron depends on that wave vector, as the momentum of one electron is proportional to k. So p is proportional to the value of the wave vector. So in this case, as the electron moves through the system, we have two constants of motion. One is the energy, the other one is the its momentum, because the Schrödinger problem is in this case without the contribution of any potential. So we have a translation, we have invariance under translations. So due to that, P is constant during the motion of the electron. So again, in this case, this is equal to the velocity times the mass of the electron. And just a comment that I didn't present you before, I just add that now. The Fermi sphere is actually a sphere. No. Again, if t is equal to 0, then if I want to plot in this diagram the occupancy of the levels, then I plot a sphere, and that's all. Because as soon as the energy is larger than EF, then the occupancy is equal to 0. But if t is not equal to 0, but is larger than 0, then if I want to plot in the same diagram the, let's say, the equivalent of the occupancy of the levels, I have to plot a sphere, but the surface of that sphere is no more, let's say, a mathematical surface, but has a sort of width, because the occupancy does not switch from 1 to 0 in just one level, but switches from 1 to 0 into a number of levels that is of the order of kt. So due to that, here, when t is different from 0, let's say, the surface of that sphere has a thickness, because that goes smoothly from the occupancy goes smoothly from 1 to 0. So again, that is not a strictly, let's say, a surface that has no thickness, but is a surface that has an intrinsic thickness that is proportional to kT. So when T is larger than 0 Kelvin, then the Fermi so there's a sort of thickness of the surface of a sphere due to the fact that if you make, let's say, a cross section of that sphere, what you expect to observe is the dependence of the Fermi-Dirac distribution over the energy, as in the case of the free electrons, as or in the Sommerfeld model, as you move along, let's say, a radius of that sphere, that you at the same time change the energy. So you switch from low energy levels to high energy levels. So that sphere has a sort of thickness. Okay. And yeah, concerning the conductivity properties of the electrons, what we saw is that we find exactly the Drude results, and we obtain those results as the underlying physics that we use here to handle the effects of any external field is the same physics that Drude used, so second law of dynamics. So in this case, no novelty from switching from the Drude picture to the Sommerfeld picture. One additional novelty appears when we consider the specific heat, as in the case of the Sommerfeld picture, the specific heat is proportional to T. That is not the leading term in the experimental dependence of CV as a function of T, but is one of the dependencies that you observe when you actually measure the dependence of the specific heat on temperature. So again, we have not been able to explain the full dependence of CV as a function of T, but at least we have been able to, let's say, single out one of the contributions of the specific heat that are actually measured when you go to the lab. So not the full dependence, but something that is physically reasonable and in agreement with the results that you obtain when you again make the experiment and measure the actual dependence of CV as a function of the temperature. Okay, so that is the, let's say, situation where we are now. At this point, I just would like to summarize what is missing before switching to the new approach for the description of the electronic properties. And I do something just like the previous Monday. So more or less, I will go on at, let's say, until 10:20. Then I make the break, and then I make the last part of the lesson. So in this case, let's say, what is the situation now? The situation is that we consider free and independent electrons. At the moment, we are not able to justify why the electrons are free, and we are not able to justify why the electrons should be independent. So those are just two hypotheses that we may not justify from the physical point of view, but the main justification is, let's say, mathematical. Let's say, if you consider the electrons are free and independent, from the mathematical point of view, you have to solve a Schrödinger equation that is quite easy quite easy to solve because you have no potential, you are just plane waves. So from the point of view of the mathematical complexity of the problem, that is quite low, because again, that is just the wave function that describes the electron is just a plane wave. So the problem is not complex. And in particular, the fact that we consider the electrons to be independent means that we may use a wave function for the electron that is a wave function that depends just on the coordinate of one electron. Because if you consider that the electrons are not independent, you need to use just one wave function depending on the coordinates of all the electrons, because you need to consider interaction between the electrons. So the position of one depends on the position of all the other electrons. So huge complexity from the mathematical point of view. So for the moment, those two hypotheses come from the, let's say, classic ideal gas approach that was used at the beginning from Drude, and also from a combination of mathematical capability to handle the problem that we have to consider. So again, no physical motivation behind those hypotheses at the moment. And the other thing, the other approach that is used by both by Drude and by Sommerfeld is the relaxation time approximation that is related to the description of, let's say, a collision between the electron and something, but at the moment we do not know what is this something. So for the moment, we know that we need collisions to, let's say, justify resistivity. We need those collisions as a mechanism to restore the equilibrium if something deviates the system from the equilibrium. But at the moment, we do not know what is the physical motivation behind the presence of the collisions. So even in this case, we use an hypothesis, but we are not able to find a physical explanation for that hypothesis. The other thing is that both Drude and Sommerfeld decided to describe metals. So they say, okay, I have 3 electrons moving in the system. But in principle, if I want a model that describes a system, the decision of having in front of us a metal or a semiconductor or an insulator should not be depending on us, but should be depending on the model. So in principle, it's the model that has to tell me that I have a metal in front of me or an insulator. That should not be a decision that is, let's say, on you. Because again, is the model that should point out if you have, what is the electronic behavior of the system that you have in front of. So why metals are metals? And the same question can be used for insulators and for semiconductors. So for the moment, we have not a physical motivation behind that justifies the electronic properties of the systems we are trying to investigate. So at this point, one should try to relax one of the hypotheses that are quite restrictive concerning the approach that we use to the description of the solid state. And this point is, what is the hypothesis that I should try to relax? The main hypotheses are free and independent. So if I relax the free electron approximation, then I should include the lattice contribution. At this point, we are at the end of the 20s in the previous century. The Bragg experiment was performed, and also the Rutherford experiment was performed. So they knew that the main part of the mass of the atom was located in the nucleus, and that the position of the nuclei was not random, but was but followed a specific pattern that was described by the um, Bravais lattice of the system. So they knew that there was a lattice. So at this point, you need to include the contribution of the lattice in the system. So if we follow that street, that road, let's say, I hope that in English we say that in the same way, you have to solve a Schrödinger equation where H is not just the kinetic term, but is also, but includes also U, or U is the potential energy due to the interaction between one electron and the lattice. Yeah, when you studied the Bravais lattice, which symbol did you use to indicate the general vector belonging to the Bravais lattice? Was capital R or something else? Okay, so let's say if R is an arbitrary vector belonging to the Bravais lattice, U of R, that, so in this case depends on the coordinate of the electron, is something that is so ZA E squared is the product of minus E, that is the charge of the electron, and ZA times E, that is the positive charge of the ion. So in the system, using this picture, we have ions whose charge is exactly equal to the number of electrons that they have shared with the solid to make the to give what is in the picture of Drude and Sommerfeld described as conduction electrons. The minus sign that you have in front of the equation is due to the fact that the charge of the ion is different from the charge as an opposite side with respect to the charge of the electron. And then we should divide by the distance between the position of the electron and the position of the ion we consider. And the summing over R means the summing over the lattice. This is the, let's say, simplest picture. So in this picture, the ion is just a point charge whose charge is plus ZAE, sorry, and the electron is another point charge whose charge is minus E, and those two charges are interacting through the Coulomb potential in vacuum for the moment. So I just wrote E0 here to stress the fact that we're still supposed to be in vacuum. So this is, let's say, the simplest possible picture you may use to describe U of R. In general, the only thing we need to know concerning U is just the fact that that depends only on the coordinate of the electron. So the position of the ions is fixed. So once you know the position of those, then at that point, U depends only on where the electron is with respect to the lattice. So in this picture, so we just remove the free electron picture. The problem is again a one-body problem. That means whatever the shape of U, you just need to consider the wave function of one electron. Differently, if we relax the independent electron approximation, then we switch from a picture where we use the wave function of just one electron to solve the problem to a picture where we need to use a wave function where we have the coordinates of all the electrons, because in this picture, so the electrons are no more independent, the position of one electron affects the position of all the other electrons. So the single wave function needs to include the contribution of all the electrons. Considering the fact that if we have a three-body problem, we have some difficulties in solving the problem. Here, n is not 3, but is of the order of 10 to the 28. So that is a huge number of coordinates. So this means that the problem cannot be solved. At the end, we will try to solve that, but we will use some approximations. So here you have a huge mathematical complexity. But apart from the complexity, is there a physical indication of what is the, let's say, trajectory you should follow? So is it better to relax the free electron approximation or to relax the independent electron approximation? At the beginning of the 19th century, they discovered the superconductivity. At this time, so in the 20s, 30s, there was no explanation of why a system should become superconductive. But what they observed was that if you know that system A is a superconductor below a given temperature, and you replace the ions of that system by isotopes. So, for instance, you have, what is the name of that? I'm not able to recall the name of the typical superconductor, sorry. So if you have that metal, that the first one was mercury. So the first experiment was done on mercury. So if you pick up the system you are using, you substitute some of the some of the atoms over that system with isotopes. So what you change is just the mass of the nucleus, not the charge of the nucleus. Then you make again the experiment and you measure the superconductivity properties of this new system. You find that the two systems both, let's say, both display superconductivity, so that is fine. But for instance, the transition temperature is different. As the superconductivity is a problem related to conduction, because at some point the system, this resistivity drops to 0, so it's something related to electrons. If you change the mass of the atom, this means that you are not changing the electronic properties, but you are changing just the mass of the nucleus. So in this case, you are affecting the lattice, not the electrons. You're just doing something to the lattice. And this action on the lattice produces an effect on the conductivity. So the idea was maybe the lattice may have an impact on the conductivity of the system. So this is a way to say, let's try to relax at first the hypothesis concerning free electrons. So let's start to consider the fact that the electrons are not moving in an empty space, let's say, where the potential is constant, but let's suppose that the electrons are moving in a space where you actually have a potential that is, in this case, the potential due to the ions that you have in the system. And let's try to include that potential in the Schrödinger equation of the electrons, and also in the wave function of the electrons, because if that Hamiltonian has a solution, that solution needs to include the contribution of the ions. So the idea was at the beginning to relax this hypothesis, and for sure there was also a situation related also to the mathematical complexity, because if you relax the free electron approximation, then you have just a one-body problem. So something that, let's say, in principle may be difficult to solve, but it's for sure easier to solve with respect to the many-body problem that you have when you consider an electronic wave function that in principle should depend on the coordinates of all the electrons that you have in the system. So the first step was remove this hypothesis and consider the Bravais lattice as a structure, as a mathematical structure that describes the actual position of the ions within the system. In this case, the let's say the following step is the one concerning the solution of the Schrödinger equation in case H is the kinetic term plus the potential term. For the moment, I would not like to discuss the actual expression of U, as I will give you an actual expression of that U later in the next weeks. So for the moment, the only thing we need to know to solve everything here is that U is a potential that has the same periodicity of the Bravais lattice. That is the only thing we need to know now. The actual shape, again, will be presented in the next weeks. At this point, I need to recall something that you have already met, I think, during the Struttura della Materia 2, that is the block theorem. Okay, the question, let's say, in the previous years, I used to demonstrate the theorem, all the details and so on, but maybe this is a sort of repetition for you because you have already studied that 4 months ago. So the proposal is, I will not demonstrate the theorem, I will just recall the points that then I need to use in the next weeks and in the rest of the class for the presentation of all the other models, because they heavily rely on the description or on the, consequences and on the features of the electronic levels when we consider the block theorem. So I will just recall one detail of the demonstration because I need that to demonstrate one property of the wave function, but then I will skip the demonstration. I will also, let's say, I just take the occasion to say that I will not ask you, please demonstrate the block theorem during the examination. So I will not ask that. I just make this proposal to you, please have a look at the demonstration, because yeah, it's true that I will not ask you to do the demonstration during the examination, but some details of the demonstration sometimes are recalled during the examinations. So please just have a check on that. Just remember the starting point, the steps, and the final conclusion. Again, to have that in mind in case the discussion will consider also some the topics of some details concerning the calculation. And yeah, since now is nearly 15 past 10, and let's say the theorem is just one line, but then I have to make comments, details, physical meaning, and so on. So if for you is fine, I would like to make a break now, and then after the break, I make a full discussion concerning the theorem, consequences, details, and so on. Do you have questions concerning what I told you up to now? Okay, if there are no questions, then I now stop the registration and we'll go on after the break.